Hello and welcome back to Calculus 3. Chapter 14 on vector fields. So the first lecture is on vector fields. And this one will help you understand, for instance, wind and flow of a liquid or something. It's interesting. So what do we have? We have a whole bunch of vectors going somewhere. So each point in space is going to have a vector associated to it. You want to understand this through the wind? It's very simple. Every particle, every air particle, because of the difference of pressure, is moving due north, let's say, and you have a wind. Take that fan, turn the fan on. You're going to feel the wind, right? All of the particles in the air are pushed by the blade towards you. So we use vector fields to describe that, because to each particle in space you assign the vector in which direction you want that particle to go to, or in which you describe the motion of that particle through that vector. So which way it's going. Now this is obviously not only for wind or liquids. You can talk about electrical field, magnetic field, gravitational field, any other force fields out there. There are many applications for something like this. So right now we are sitting in gravitational field. The mass of the planet is much larger than mass on any object that we are handling, and the mass of the planet is curving the space-time, so we perceive that as attraction between the two objects. So in order for this to fall, it has to be in gravitational field, attracted by something, right? It's lame to say that way, but that's what we perceive, so we'll say it that way. So what happens is, if I let go of the object, it will fall. But this field, gravitational field, is not only here where I hold the object. If I move the object, that field is here and here and here. No matter where I place this object, it will always be in the gravitational pool of the planet, and when you let go, right, it goes down, no matter where you put it. So field is not something that it's local, right? It's really wide, it's big. And there are different kinds of fields. We have, we'll see, rotational fields, right? That will make the stuff rotate. We'll have radial fields, right? That push the stuff outward. We have the flow and shear and all of these different types of fields. This is extremely important in many aspects of the design. Here are examples that are really nice in the book. What we have over here is you're looking at hurricane or tornado or something. See all the vectors here? Vector field is something that you can measure, because those are vectors and motion and velocity. So you take those little probes and you toss them into the tornado, and they will spin with the wind, and they send you the reading of the velocity, how fast they're moving, and so on. You can get the reading for stuff like that. And then you can understand, you can see the motion this way, you can see this motion going that way, you can see this one spinning on the top as well. So there are a lot of things that you can a lot of different vector fields that you can consider in something like that, right? It's not just like the wind, oh, goes this way, right, straight. This could be some kind of a heat flow, right, through the object. You see these edges over here are cold, right, because they're at the corners, and the rest is hot, could be that. Magnetic field, right, magnetic field, when the magnet is the strongest, obviously the closest you are, it gets weaker, just like gravity or electrical field. The further away, they all drop off with a square of the distance. So the further away you are, right? And then you need to learn in physical reality, right? If you go drive your spaceship that you built close to the sun, you burn. Let's say you go, I don't know.
I feel like the story's been told before.
Like 1,000 miles away from the sun, you burn.
Yeah.
No, you don't. Heat doesn't transfer to vacuum, so you don't. See, that's one thing that you have to learn, right? That you have to have a medium for. So you watch Star Wars movie and they're amazing. But they're amazing, and then you see all these space battles, and what do you hear? There is no air to transfer the pew-pew sound. That is all special effects. In what you would see in space is just little lights, right? Because the light can travel through the vacuum, the sound cannot. Because the waves for sound, the earthquake, right, has to have earth to travel through, right? You're gonna hear better under the water or on the sun, on the surface in the air. Underwater, you're going to hear much better underwater than even though we're not evolved to listen underwater because it's a denser environment. And it's, try it. Fill your bathtub, try to keep your nose above, right? And then do the little bang on the side. It will be so much louder than when you get out and you bang the same, right? So the medium is important. But the vector fields, we're just going to travel through stuff, right? So the wind is going to travel. Is there a wind in space? No, no air, right? So you can't have wind. But you do have objects rotating, spinning, and moving, and so on. So now we're going to define a vector field. Vector field is a function, right? And then we'll take a look at some examples, and believe it or not, that's a lecture. You just need to understand what this is. We will use vector fields for the rest of the chapter. Today is just a definition in 14.1 is just definition. So, definition of a vector field. Why are all my colors different now? Just the regular red? That's a regular red. Definition. So, let F and G be defined on region R of R2. So that means these are just standard functions, y equals f of x, y equals g of x in 2D, because it's R2. A vector field in R2 is a function that assigns to each point of R a vector fxy gxy written f with the arrow on top because it's a vector field of xy. Now they will use bold in a book. We use arrow above for vectors. Is f xy g xy or f of xy is equal to fxy I with a hat, it's a unit vector, g xy with the j, the hat, is the unit vector. This is the definition. Vector field is a function. What do we know from our previous life in pre-calculus, then calculus 1, then calculus 3? We know definition of a function. Function is a rule which assigns to each point in x a unique y, right? In Calc 3, multivariable function. Multivariable function is a function that is a rule which assigns to each point in space a unique z or w or something in a range. And now we are upgrading that. Instead of getting a single unit value like y or z, we are actually getting a vector as the answer. So to each point in space, we are assigning a vector. It is very simple to understand this concept if you just pay attention for a second. Let's say that your vector field f xy is given as 3x comma 6, whatever. There you go. So this first one over here is f, and the second one is g. I hate this green color. Darker green. So this is your f, this is your g. I'm not sure how all of these changed. Anyway. All right. So what do I have? If I want to graph this, we will use our standard xy because this is a 2D example, right? And now I want to check what is happening at point 0, 0. What's happening at the point 0, 0? Well, 0, 6, exactly. 0, 6 is happening at that point. So we go to 0, 0. This is where our vector starts. And we go 2, 3, 4, 5, 6. So the vector is this. This is our first vector. What is happening at 1, 1? There's the point 1, 1 on our, right? So what do I have? I have 3, 6. Great. So starting point is where you start drawing the vector. Then you have to count 3, 6 from there. 1, 2, 3, 1, 2, 3, 4, 5, 6. This is the vector that will be there for 1, 1. What is happening for, I don't know, -2, 1? -6, 6. Because, and that's a vector. Because you will take the x coordinate, which is -2, plug it there in the equation for x, and you will get 3 times -2 is 6, so -6, 6. So that's 1, 2, 3, 4, 5, 6. So negatives. Oh no, wait, hold on. -2, 1. -2, 1 is here. So 1, 2, 3, 4, 5, 6, and then 2, 3, 4, 5, 6. So there it is. I don't know, fireworks? It's gonna go like this. That's what it's going to look like. Fireworks? I don't know, right? You can literally put whatever you want, right, in these vector. Any formulas. You can use x squared. You can use 1 over ex. You can put whatever. You will use x and y coordinates to compute the value. So let's see what are the standard ones that we want. So we want to take a look at the nice one, this one. Well, first, do this. Negative y, x. So we have a vector field. Don't forget the arrow above f. Vector field that it's given as negative y, x. So now I want to graph that on xy plane. I start with checking point 0, 0. When I plug in 0, 0, 0 for x and 0 for y, I do get vector 0, 0, which is a 0 vector, so I just get a point. Nothing special. Great. How about 1, 0? What do I have? 1, 0. Well, this is where you have to just do some chasing, right? Your x is 1, so if x is 1, the 1 goes there. And your y is 0, so you get 0, 1. Are we all agreeing on that? Let me point my finger. So this is your xy. Your x is 1, so you plug 1 for x, which gives you 1 over there. And your y is 0, you plug that into y, and you get 0 there. So this x and y locations have nothing to do with xy locations here. These are determined by what the functions, and as you can see, they switch them over there. So x is 1, you plug that into x, and you get 1 over there. Y is a 0, you plug that into y, and you get 0 there. So now you have to go to the point 1, 0, and draw a vector 0, 1. There we go. So 1, 0 is 1 on x-axis, and you draw vector 0, 1. How about the point 0, 1? Well, your x is 0. It's going to be 0 there. Your y is 1, so it's negative 1. Oh, okay. That one is this. The point negative 1, 0 is...
Does it go like from that point, like so if we change like 0, 0 to that point, because if you have 0, 1 going to negative 1, 0, wouldn't that be like diagonal?
If we use 1, 1, it would be. We'll deal with that. And finally 0, negative 1. Plug in negative 1 for x. That's a negative 1 there. No. X is equal to 0. So that's a 0. Negative 1, that's a 1. Now, let's try 2, 2. So x is becoming a 2 and y is a negative 2. So you're starting at 2, 2, and you have to go negative 2 on x and then positive 2 on y. So this is your vector, which means that this one will go like that. This one will go like this. And this one will go like that. At this point it will go up. At this point will go this way. At this point will go down. Oh no, at this point will go this way. It's off. Hold on. Much better. 1, 2, 1, 2, 1, 2, 1, 2. Good. Do we see what's happening here? Rotation. You see that all the vectors are pushing for this to rotate? Counterclockwise? You can calculate this at every point. All of the vectors will land so this rotates. Yeah. Rotational magnetic field to create electrical motor, electrical generator. All right? Vector field F is given as xy. Zero, zero will give us 0, 0 origin, right? One, 0 gives us vector 1, 0. Zero, 1 gives us vector 0, 1. So now, all of these vectors, I'm just going to draw a whole bunch of them. And then there'll be vectors in between like that as well. You can compute every single one of these because you can pick any point you want and plug in. Does this look like an explosion, right? In all directions? You can think of this also as a sun that radially gives energy off in all directions. Now, sun is a great example for the 3D radial field. But if you are to look at the cross section of a sun, the way the kids draw sun when they do this. Right, and they make it smiling. The kids don't know it, but they are drawing a radial field because each one of these lines is actually energy out, and we call that radial field. So this is what the radial field is. So you have some kind of source that radiates something out, right? So as I said, in terms of an explosion, right, it's the energy pushing out. In terms of the sun, is what? It's not heat. We talked about it, right? The heat can't transfer to vacuum. The sun is hot, right? 10.4 million degrees. So, bit hot, sure. Would boil your egg quickly, right? What is the sun giving off?
Heat.
Yeah, but heat doesn't transfer through the radiation, yes. Radiation, UV, X radiation and all that, which hits our atmosphere, converts into heat. Okay? The energy, what is heat? Does anyone know what the heat is? Yeah, but, no. What is heat? Like, feel your hands now, everyone. Feel your hands right now, like this. Feel. Right? Now, let's go. Why are they becoming hotter now? Yeah, friction. But what did we introduce? We introduced energy in terms of what kind of energy I want to hear. Kinetic energy, motion, guys. Rapid motion. Heat is rapid motion. All right? You have a heightened energy state with kinetic energy. More bumps between the molecules and particles. They produce that. It's manifested as heat. All right? So that's what we have. So when radiation that can travel, right, because those are the waves, like light waves that can travel through vacuum, which is space, hits the atmosphere, it starts bombarding and hitting the atmosphere, and then that heats up and creates what we perceive as heat from the sun. But what is the first thing that happens to you when you go above atmosphere level without protection? You freeze to death. Wouldn't that be hotter because you're closer that much to the sun? No. You instantly freeze to death. There is no heat transfer between sun and earth. It's vacuum. Heat doesn't transfer to vacuum. That's why you can make a fusion reactor with 150 million degrees inside that's 15 times hotter than the sun. We have those built on the planet. Fusion reactor with a plasma that's 150 million degrees. Remember, sun is 10.4. And it's perfectly fine to be in the room next to it because 150 million degrees is suspended in vacuum. And that plasma that can melt everything, including the planet, right, is not doing anything because it's suspended in vacuum, held by magnetic field. So no heat transfer through vacuum. And that's the reason why fusion reactors are much safer than the fission reactors, right? Fission reactor is splitting the atoms, so it's actually the way the nuclear bombs work. And so fission reactor, which is what we have now, and the nuclear bombs work on the same principle. Fusion is completely different. So the fusion is putting things together. Fission is splitting things apart. And you can chain reaction and uncontrollably chain reaction. So when the nuclear bomb goes off, all that destruction is from less than 5% of the chain reaction that actually happens. It's very inefficient, right? But it's a lot of energy. No, it is. It is very inefficient. Yeah. It's the strongest weapon we have, but considering that it's less than 5% efficiency, it's worse than a car. Is there anything else I want to talk about? We talked about radial field.
So the second coordinate vector, so we move those coordinates away from the initial point, or we move to those coordinates?
You start at the initial point, okay, and then you count the vector you have. Okay. So the previous example was much better, right? So if I have a coordinate 1, 0, right? It's 1, 0, and then you do the flip over here. It becomes 0, 1. So 0, 1. So we start at the point and we go 0, 1. Because 0, 1 vector is here, right? That's where the 0, 1.
So you basically just like change the origin and then move to that point.
Yes, this becomes your origin for you to draw this vector. That's a very good way to put it. Nice. So this becomes your origin for you to draw the vector. So each point is the origin for the new coordinate system in which you will draw the vector in its original state. Very good. 3D. 3D VFs. What are the 3D VFs? That's the 3D vector fields. Same stuff. We're just going to say that the vector field in 3D, x, y, z, is going to be given by FGH. F, x, y, z, G, x, y, z, and H, x, y, z. And that would be our three-dimensional vector field. Again, if you need more and deeper explanations and things, just look at the older streams. We are a little bit in a rush, so we're doing less examples than I would like to do. But as I said, every lecture that I have is different because I don't use any scripts or anything. I just do whatever. So between different 14.1s back in the channel, you'll find different examples every time. Here is the 3D stuff. You have three different examples here. I'm going to start with the sun, radial field, right here. I hope you can see that there is origin, which is source, radiating in all directions, right? So that's the, right, that's that one. This one, do we see that all of this stuff emerges out of the, we call it like fireworks maybe, but fireworks still has a source that was much closer in. This is already the later stage of the fireworks when it's spread, right? But we can see the, do we see the spread on this one? Do we all see the flow? I don't care whether this is a water pipe, a gasoline pipe, or a blood vessel, right? Please note that the vectors in the middle are longer than the vectors on the sides. Why is that? Friction, thank you. Right? The friction with the walls is slowing down the liquid on the outer, and the flow in the middle is the fastest. Right? Garden hose, or the pump for the gas, or your blood vessels. What happens with the blood clot? You block off this much. What happens with the, so your pump is going to pump with the same strength. You are trying to squeeze more volume. You're trying to squeeze same volume of blood through smaller surface area. Well, if the walls are not strong enough, you need enough carrots and broccoli, right? They burst right there, right? And there is your internal bleeding. So these are the things that they all make sense when you take a look at mathematics, right? So the flow has the strongest inside, right? The most force in the middle, and then the closer you are to the walls, the friction happens with the walls, slows the liquid down. Any buildup and any stuff in arteries and veins obviously is going to restrict that flow and make it worse. There is a nicer 2D example in this lecture for the flow. There it is. We have a rotational field, the one that I drew. They just have more vectors. It looks better. But here's your flow in 2D. So this is your 3D flow, just cut in half. You take z value out, 1 minus y squared comma 0, right? If you want to make this to be flow like that, you will have it 0, 1 minus x squared, and we'll go up. You can play with the thing. We see the fastest, right, strongest flow in the middle, and then flow at the wall, 0, right? Because the walls don't flow. When you are at 1 for y, 1 for y, squared is 1, 1 minus 1 is 0, so 0, 0, no flow on the wall. And then it gradually becomes stronger, strongest in the middle, then falls off back to 0 for the flow. So it's, I don't know, I see this as interesting, just to see how mathematical equations like really explain and show. Some of the radial fields, they are x, y. Tangent, 3D fields, and now gradient and potential function, and the lecture is over. So, gradient field. We know that the gradient is what?
Like R the magnitude r prime?
No, that's the tangent.
Vector from each partial derivative.
Yes, it's the vector from partial derivatives. Vector of partial derivatives. So gradient is a vector made of partial derivatives. So that gives you the vector field, because at each point your gradient will have a different value, which is a different vector. So great, it fits the definition of the vector fields. So now we can create the vector field using the gradient function as well. So the let me just see if we can find, there you go. So definition for the gradient. Oh, this was also definition for the 3D function. Gradient field and potential function. And more on this in 14.3. More on this stuff that I'm writing now. So what do I have? Let phi, so that's the Greek letter phi. Let phi be differentiable on a region. Let phi be a function. There we go. Differentiable on either R2 or R3. Works for all of them. Well, it works for R4 and R10, but whatever. The vector field F equals gradient of phi is the gradient field and the function phi is a potential function of f. All right. So let phi be a function differentiable on R2 or R3, the vector field f. What does this mean? Give me any scalar function that you guys know. You know which ones I think of? fxy. Give me anything. X squared plus y squared. Fine. There you go. This is what we would call phi. What is the gradient of f? xy. We are back now to chapter 12, right? So what is this? 2x, 2y. That thingy is your f. See that? We didn't learn anything new other than new names, right? So we took the same concept from, that you know, from chapter 12 and just gave it a new name. Because now we can take any function and generate the vector field. Now, for science, this is insanely important. Remember what I said with those little probes? What do you do with the little probes? You toss them into the tornado, hurricane, right? And then they give you data. They're going to give you data for vector field. 14.3 is going to teach you the method which you can use to go, when you have the vector field, find the potential function. When we have these things, we can make stuff. All right? So when we have a function, we can build things. All of you call them formulas in physics and engineering, right? You measure the field, because field is something that our equipment can detect. You measure the field, then you will use 14.3 to come up with a function, potential function, then you will rename that into a formula, and then with the formula you can make stuff. Electrical engineering, mechanical engineering, applied physics, all of that stuff. That's 14.1. We now have seen ties, back to all of the stuff. Take a 2-minute break, and then line integrals, 14.2. Bye.